And so it comes from drawing the angle accurately when you're creating these pictures. And so there's really just like two cases you have to know, which is like the 45-degree case, or the second one is the 30-60 case. Because the 30-60 triangle, they're coming from the same triangle, just, oriented a little differently. And then there's the 45-degree case. And so if you look at these, like the 30 versus the 60-degree angle, you see that we have the same values, but they're swapped, right? And it has to come from which of the legs are longer, like which leg is longer than the other. And so I have this diagram here that I created where there is like the two cases drawn out. So we have our 45, 45, 90 case and our 30, 60, 90 case. So if we look at the 45, 45 case, if you're have some sort of increment of 45 degrees, your coordinate points are the same because these leg lengths are the same. And that was the property of this 45, 45 special right triangle. And so all you have to do is like, these are going to be your coordinate points, but switch this, like change the signs accordingly, like depending on which quadrant the 45-degree angle is in. For the 30, 60, 90 case, here are the two pictures of like where the 30-degree angle is in the bottom left corner versus the 60-degree angle. And if you draw these accurately, like it's better to kind of exaggerate it more, like to see it. You can see like this 30-degree angle, the steepness of it is it's less steep than like if you have a 60-degree angle. And so if you draw it accurately or even with a little bit of an exaggeration to the angle, you can clearly see between the two legs which leg is longer than the other. And so the longer leg gets the square root of 3/2 value, and the shorter leg gets the 1/2 value. And that's because, like, if you look at the decimal values, like root 3/2 is a larger value, which is going to give you a longer leg than 1/2. Right. So let's go ahead and practice this in example 3. And you can see with this example, we're going to be looking at some increments of the common angles, but the measurements, you can see that we're starting to have like some negative measurements or like large angle measures. All right, so let's just start off with example 3A. We're finding the sine of negative 45 degrees. So the procedure of this is like, first draw out the angle and then create the right triangle. So you see what kind of, like, if it is a 45-degree, 45-45 triangle or a 30-60 triangle, and then find out the values, if it's root 2/2, or you have to look at the longer versus the shorter leg for the 30-60. All right, so since this angle is negative 45 degrees, we're going to start measuring. We would measure 45 degrees clockwise because of the negative, right? So this would be clockwise, and we stop. That would give us negative 45 degrees. And so we're in the 45-45 case. So let's go ahead and draw our right triangle. So you always draw where the terminating point is, draw to the x-axis. So this time it's going up to the x-axis. And so here's our right triangle, and our legs are the same length. So that's going to be square root of 2/2. And then on x, and then on y, it has to be negative root 2/2 because the angle terminated in quadrant 4. All right. And these coordinate points, our x coordinate would be like the cosine. If we needed that, the y is the sine. So since we want the sine, we're going to take our y coordinate. So sine of negative 45 degrees is negative square root of 2 over 2. All right, so let's try some more. Example B, we have cosine of negative 90 degrees. So this is a quadrantal angle. So if we map out this picture going around the unit circle, we would go clockwise 90 degrees and stop. So that would be negative 90 degrees. And we're on the unit circle. So where we stop here on the unit circle is 0, -1 as a coordinate point. And since we want cosine, we would take the x coordinate. So cosine of negative 90 degrees is equal to 0. All right, so secant of negative 300 degrees, we're going to have to use some identities here because secant is the reciprocal of cosine. Anyway, so first, just map out the angle. So negative 300 degrees. All right, so negative 300 degrees. All right, so if we start drawing this, all right, so we would go clockwise. So if we go clockwise, like a 3/4 turn clockwise, that would be negative 270. Right, so remember, usually for 270, the location, if you're going in the positive orientation counterclockwise, it's a 3/4 turn. But since we're going to go clockwise because it's negative, it's going to be a clockwise 3/4 turn. And then the remaining amount to get to negative 300 is that we have to go 30 degrees more, right? So 30 degrees more clockwise. Gives us a terminating side of, that's drawn in blue. And so when we create our right triangle, draw down to the x-axis, this becomes a 60-degree angle that's inside of the triangle. And if we look at the two leg lengths, because it's, more exaggerated here, this coordinate point is positive 1/2, right? Because the legs, we look at the legs here, this horizontal leg is shorter than the vertical leg. And so that's shorter gets 1/2, longer gets 3 over 2. All right, so we know that 1/2 would be cosine. Okay, so this This 1/2 would be the cosine of negative 300 degrees, and the y would be sine of negative 300 degrees. So we have to find the secant. Okay, so we can use the idea of reciprocals. We know that secant is the reciprocal of cosine, right? So if we look at our cosine angle, if just take the reciprocal, like flip the 1/2, right? So that would be 2 over 1, which is just 2. Right, so if we wanted to find the cosecant of negative 300 degrees. So cosecant is the reciprocal of sine. So you have to take the y coordinate and flip it. And then you have to end up rationalizing it because the square root of 3 ends up in the denominator. Okay, so let's try the next one, sine of 420 degrees. All right, so sine of 420, like 420 is more than 360, like more than one full loop around. Okay, so let's see right here, 420 degrees is 360, and then how much more? 120? Wait. 60, right? Let's see, 420, and then subtract out 360 gives us 60 degrees as the remaining amount. Okay, so when we draw this picture then we would go one full loop around counterclockwise. There's 360 and then 60 degrees more, and we would stop. So I like to exaggerate a little more like this. Okay. So that would be 420 degrees of a rotation. And then where we stopped and draw down to the x-axis, right? So we would have the shorter leg is the x coordinate, which is 1/2. The longer leg is square root of 3/2. So if we want the sine, that would be our y coordinate. Okay, so sine of 420 degrees is equal to square root of 3/2. All right. So like if you guys have any questions, like, or you wanted to see something, like write it out, just like, please feel free to interrupt me and ask the question. I'd be like really happy to answer any questions, or you can like type it in the chat. All right, so the last one. Oh, and you can also ask me to repeat something if you missed it. All right, so 840 degrees. So 2 loops around the circle, like 360 and another 360 gives us 720. So let's kind of break this down. 840 degrees, that would be 2 loops around. So 2 times 360, which is 720. And then plus how much more than 720? 120 more. So it's like 720 plus 120 would give us 840. So so knowing that, let's draw our picture. Okay, so let's go twice around. 1, 2. Okay, so right now we're at 720 and we're going counterclockwise because it's a positive angle. And then we have to go 120, which is 90 plus 30. So another 90 and then another 30, and we stop. Oops. And draw our terminal side. So this was a 840 degree angle. And then there's our terminating side, there's our coordinate point, and drop down the leg to the x-axis. So our shorter leg is on x, so that gets negative 1/2. Okay, so negative 1/2, and our y gets the longer leg, which is positive square root of 3 over 2. So now we have to take the tangent, right? And the definition of the tangent is you take your y coordinate divided by the x coordinate. So tangent tangent of 840 degrees is y divided by x. Okay, so we take our y coordinate, root 3 over 2, divided by our x coordinate, negative 1/2. And we have to simplify that out. We have to flip the denominator and multiply by the numerator, right? To get rid of the complex fraction. So flip and multiply. All right, so then this is square root of 3 over 2 times negative 2 over 1. So 2's cancel out, comes out to be the square root of 3. Oh, wait, negative. Okay, it was negative 2 over 1. So negative root 3 is the final answer. So tangent of 840 degrees is equal to negative square root of 3. All right, any questions here? All right, so if this one was asking for cotangent of 840 degrees, then the definition of cotangent is that you take the x coordinate and divide it by the y coordinate. Right, so if you are given a cotangent, that's what you have to do.
I have a question.
Yeah, Isabella?
So do we always flip and multiply, or I didn't get that flip?
Oh, so if you ever have like a complex fraction, like, you know, there's a fraction, like a fraction divided by another fraction. If you wanted to simplify that, then yeah, you take the denominator and you flip the denominator and then multiply it by the numerator. So that's like an algebraic technique. So yes, you would always do that if you have a fraction in the denominator.
Okay, thank you.
Yeah. Or even actually, even in the numerator. So for example, if we had something like 2 divided by, oh wait, no, sorry. 1/2 divided by 3, like that, then you would also, to simplify this, you would flip the denominator and then multiply it by the numerator. So this is like, you would have to write it as 3 over 1. So then this is 1/2 times, flip that to 1/3. So it comes out to be 1/6.
Okay, got it. Thank you.
All right. So using a calculator to find values, we've been doing this with some of the previous examples. But like later in today's class, we're gonna find out like that there's another way to measure angles. It's called a radian measure. So like, you know, we've been measuring these angles with using a degree measure, and we'll introduce another way to measure called a radian measure. And so on your calculator, there's two different modes. There's a degree mode and a radian mode. And so it's like they have to know exactly what the angle measure is in here in order to do the correct calculation, because it's like, think of like feet versus inches, right? Like they have to know how this is being measured to do the correct calculation. And so that's the different modes on your calculator. So if you have a regular calculator that you're using, like a scientific calculator, there's a mode button. And then in the mode button, you can see like degree versus radian. And then you would have to like change the mode accordingly. So like if you look at my calculator on the screen, I have a toggle here like degree and radian. So like make sure like we're gonna have to be switching these modes a lot later in the class. Right now we're keeping it on degrees because we haven't introduced the radian measure yet. And then if you're using a different calculator, you can Google like how to change like degrees and radians, like use Google, or like, there's a settings button or something like that. All right, so we're going to use our calculator to find, if you have your notes, tangent of 50 degrees and sine of 165 degrees. And it says to round your answers to 3 decimal places. So we'll just like tangent, make sure it's in degree mode, 50, and then sine of 165. Right, and you just push enter and you should get these values. So it might seem kind of trivial, these examples, but you do want to follow along with your calculator and make sure you can get these values because like for example, if you look at right, I'm gonna change it over to the radian measure and like you can see how these values are going to change. Right? So if I go to radians, they calculate it using like 50 radians in for tangent instead of 50 degrees. And so the values change. So make sure like you're able to, like know how to use the calculator you're using and changing it, having it on the correct mode. So you know that you're on the right track and you don't get frustrated when you do your homework. All right. And since we're rounding to 3 decimal places, just use the rounding rule. It looks like for each one of these, we have to round up because since it's 3 decimal places, you look at the 4th place. If it's above 5 and above, you round it up. So this has to be bumped up to 2. And on the second one for sine of 165, yeah, that's an 8. So this is going to be bumped up to 9. All right, so this one, we'll say tangent of 50 degrees is approximately 1.192. Sine of 165 degrees is approximately 0.259. All right. So if we move on to the next section, we're going to start introducing identities, trigonometric identities. And the definition of identity is that it's an equation that is satisfied for every number for which both sides are defined. So basically an equation where if you fill in a variable, like the equation is always going to be true for that input that you put in. Or for every input, right? So here's an example of a identity. These are called the reciprocal identities, which I've touched on already, but here's the formal definition. And so here's an identity, and this is a true statement such that any alpha you plug in, like if you put in 30 degrees into these alphas, the left-hand side is going to be equal to the right-hand side. And that's why it's an identity. And so like you can change this alpha to anything like 50 degrees. And here, left-hand side is the same as the right-hand side. And so the reciprocal identities, cosecant and sine, there are reciprocals of each other. So cosecant of alpha is the same as 1 over sine. That's the definition of reciprocal, is taking 1 over that. And then secant and cosine, these are reciprocals. Cotangent and tangent are reciprocals. And then you can also say, like, go the other way and say, okay, sine is 1 over cosecant. So, I mean, you could take this equation and isolate it for sine, and you're going to get this second equation. So, like, if you work this out, like cosecant of alpha is 1 over sine, and you want to solve this for sine instead, then you can like cross multiply and say this is cosecant of alpha times sine of alpha is equal to 1. And then divide both sides by cosecant of alpha. Right. So you get that sine of alpha is 1 over cosecant of alpha, which you see over here. Right. So you can write the reciprocals for each of the trig functions. All right, so we'll go ahead and try example 1 that uses these reciprocal identities. So for A, it says here, find the value of each expression using the reciprocal identity. So for A, if we know that cosine of theta is 0.3, then what is secant of theta? Well, we know that cosine and secant are reciprocals of each other. So using the identity, we can write cosine of theta. Let's see. I'll circle the identity that I'm using. Is 1 over secant of theta. Oh, wait a minute. Oh, let's use the other one. Sorry. This one, because we're trying to find the secant knowing the cosine. So let's write, we're trying to find the unknown. So we're going to start it with the unknown. So secant of theta is equal to 1 over cosine of theta. Okay, so we know that cosine of theta is 0.3. So we're going to put in 0.3 into the denominator. So this is 1 over 0.3. And let's say we want the exact value. Okay, so exact value would be like the fraction without a decimal. And so using the definition of 0.3, that's to the 10th place, right? So that's equivalent to 3 over 10. Right, so when you have like a 100th place, like 0.05, like that, this is actually saying 5 over 100 because it's to the 100th place. That's the equivalent fractional form. All right, so then you would have to flip the denominator and multiply by the numerator. So secant of theta comes out to be 10 over 3. Okay, so part B, if we know that cotangent is 4 over 3, then what is tangent of theta? Okay, so using the reciprocal identity, the one that we're trying to find is the tangent. So let's use, I'll circle that one, the last one. Okay, so tangent of theta by the identity is 1 over cotangent of theta. All right, so since we know that the cotangent of theta is 4 over 3, we'll substitute the 4/3 in for cotangent in the denominator. And then simplify it. So tangent of theta is 3/4. Okay, so of course, like we could have said, oh, I know that these are reciprocals of each other, tangent and cotangent. So I can just flip this fraction, right? The reciprocal of 4/3 is 3/4 of what we got. But then I just wanted to show it using that identity that we just learned. All right, so we can take a look at the domain and range of our trigonometric functions. Okay, so while when you first learn about these trigonometric functions, it's kind of weird, like to understand what's going on. But these are just functions. Like you can think of y is equal to x squared. That's a function. Well, this is also, our trig functions are also functions where we have an input and an output. And so with the trig functions, the input is just a little bit different. Our input is an angle. So it's like we rotate and we input that rotation into our trig function. And the output is the ratio of the sides of the right triangle. So for example, if we had our input was 30 degrees, then we draw out this 30-degree angle. And we know that on our unit circle, those were the sides of our triangle, right triangle. And so the output we know is, if we want the sine, it's a ratio. Ratio is a fraction of two sides of the triangle, right? So since sine is right, so opposite over hypotenuse, then the opposite side is 1/2 and we divide by 1. So that's why sine of 30 degrees is 1. And so our input, or 1/2, sorry, sine of 30 degrees is 1/2, right? So this is our input was an angle, our output was comparing the opposite side to the hypotenuse, but our hypotenuse is 1. All right. So this you'll see in your homework for section 1.8, like it'll ask you for all the domain and the range for like all these different functions. But like it's hard to really understand why the domain and ranges are these ways for these functions until we go to chapter 2, where we start graphing these functions and we find out that they're waves. And then just like in college algebra, when you like graph a function like x squared, let's say like this, here's like x and y, then you can find out what the domain and range is by looking at the graph and looking at the possible x coordinates and the possible y coordinates. We're not there yet. So when you do the homework, I would just like suggest that you have this table on page 29 open, and you just kind of like match it up for the homework, and then it'll become a lot more, you'll see the reason why these are in chapter 2. But I can explain a little bit to make some sense of this. So for sine and cosine functions, you can see that the domain and ranges are like the same for sine and cosine. So like domain is all real numbers. That's negative infinity to infinity. So the domain is all the possible inputs, and our inputs are angles, right? So like just from thinking about the example that we opened up with in this class, you can see that these inputs that of the angles that we're mapping out, they're like infinite, right? We can map out an angle of negative 1,000, see where we stop and find out what the coordinate is, right? For sine. And we can do the same for cosine, and we can take it to the angles to a very large number as well. So that's why the domain, our inputs of angles are endless for sine and cosine. And the range for sine and cosine are between like all of the outputs of your coordinate points are between -1 and 1. And that makes sense as well, because I mean, we're going around this unit circle to find these values for sine and cosine. And this circle ends, it doesn't go beyond 1 or -1, right? The radius is set at 1. And if we're going around this circle, we're bounded between the -1 and 1, where you're not going to end up on the circle measuring some angle and you're out here at like -5, right? So that's why our range is bounded between -1 on 1 and 1 for sine and cosine. All right, so let's take a look at tangent of theta. So the domain for tangent is saying that your input of angles can be anything, except there's some conditions here. You cannot take tangent of 90 degrees, 270 degrees, 450 degrees, and there's infinitely many. And so for the reason of this is because when you try to find the tangent of 90 degrees, you end up with undefined. You have to divide by 0 because, like, for example, if I map out 90 degrees, we're up here at the coordinate point 0, comma 1. And so if we try to take tangent of 90 degrees, the definition is like y coordinate divided by the x coordinate. So if we took that y coordinate at the 90-degree mark and divided by the x coordinate, we get undefined. And if we go to 270, so at 270, if you rotate 270 degrees and stop, we're at the negative y-axis. That coordinate point is 0, negative 1. So tangent of 270 degrees is also y divided by the x. So y is negative 1, x is 0. We get undefined. So all of these infinite values that you see, the restriction on the theta is whenever you are rotating and you end up at the 0, 1 coordinate point, you're rotating around and you end up at the 0, negative 1 coordinate point, you always do this y divided by the x and you're going to get undefined. So that's why there are these restrictions here. And you can see the same restrictions here for secant is the same as tangent, and that's like at these poles on the y axis, you end up getting undefined at those, where you terminate that angle there for tangent and secant. And for cosecant and cotangent, those angles are undefined when you're at like the 1, 0 or negative 1, 0. That when you end up doing the division, you get, you have to divide by 0 and it's undefined. All right, and then the ranges, if we just kind of skim over the ranges for these other 4 trig functions, you can see that some of them are all real numbers. Like for tangent, the range is all real numbers. Those are all the possible outputs. And that makes sense because let's say you're at an angle over here where your value gets like your denominator on x is very close to 0. Like you end up having your output is a number and then you divide it by something very, very close to 0. That's a huge number. This is a huge number, almost infinity, right? So that's where those come from. But yeah, this is going to be a lot more clear when we start graphing these functions in chapter 2. So this is a short explanation. You'll get the full explanation later in the class. So when you do the homework, just take out this table and look at it to answer the questions. All right. So another set of identities. So like the first set we learned was the reciprocal identities. Okay, so the next one is called the quotient identities. And the quotient identities are for tangent and cotangent. So the identity goes that tangent of x is equal to the sine of x divided by cosine x. And because like tangent and cotangent are reciprocals, you could just flip this for the cotangent. That cotangent is cosine over sine. And so the reason for this, like to make some sense of this, is because, on our unit circle, how we have our x, y coordinate, and I said like your cosine is your x and your sine is your y. And by the definition of tangent is y divided by x, the y coordinate divided by the x coordinate. So if we substitute that with the sine and cosine, the y coordinate is sine, the x coordinate is cosine, and then that's how you get that quotient identity, right? And then we know that cotangent definition is x divided by y, so that ends up being cosine over sine. All right, so we can take a look at example 2 using this quotient identity as a little exercise. So if we know that cosine of theta is 5 over 13, and then we know that sine of theta comes out to 12 over 13, then what's the value of tangent? All right, so since we know the sine and cosine values, we can use this quotient identity to find out tangent. So tangent of theta, using the identity, is sine of theta divided by cosine of theta. All right, and because we know the sine of theta is 12 over 13, right? Then we can substitute 12 over 13 in the numerator. And cosine is 5 over 13. So we'll put 5 over 13 in the denominator. And then just simplify this. Right, so we have a fraction divided by another fraction. So we have to flip the denominator and multiply by the numerator. So we get 12 over 13 times 13 over 5. 13's cancel. So we end up with 12 over 5. Right, so we get that tangent of theta comes out to 12 over 5. All right, so our next set of identities is called the even and odd identities, or another way, like you might see it in the homework, it's called the negative angle identities. And here they are in the box. And what it says is like, these are relating to the even and odd functions that you might have learned, or you should have learned in college algebra or in a previous algebra class, like how there are even functions and odd functions. So a little bit of a review here to make a connection here is that like an example, a famous example of an even function is something like y is equal to x squared. And the reason why it's even is because if you graph it, we know that x squared is a parabola. And it's even because this parabola is symmetric about the y-axis. That's one of the properties of an even function, is that symmetry about the y-axis. And so the algebraic test for that, to prove if a function is even or odd, is that if you calculate f of negative x, and when you calculate that, it came out to the original function f of x, then the function is even. So for this example, on the x square, if our function, let's say here we replace the y by f of x, right? So if we do this test of the even or odd function, if you do f of negative x, then if the function is defined to be x squared, then that we replace that with our input of negative x, and then see how this becomes x squared, which is the original function that we were looking at. So then that was, if you follow the thought process here, f of negative x is equal to f of x, that's an even function. And so this is the idea that is being used for relating to our trigonometric functions. So later when we graph these functions, you'll see that cosine is actually an even function. When we graph it, you'll see that it's symmetric about the y-axis. And so because it's an even function, this thing holds true where, if our input was negative, it'll be same as if the input was positive. And that's what this, that's what this is saying, right? If the input was negative, is the same as if the input was positive. That is the property, the general property of an even function. And so they're just taking this property and applying it to the cosine function. And in turn, it also applies to its reciprocal, which is secant. All right. And so for the property of the odd functions, so the famous odd function in algebra would be the x cubed function, right? And x cubed looks like this, this one that's like highlighted, that's in quadrants 1 and 3. And the property for the symmetry, how it works for odd functions, is that it's symmetric about the origin. And so some symmetric about the origin means that you would have to take part of the graph and reflect it over the x-axis and then reflect it over the y-axis, and you'll be like lying on top of the original graph. And that is also interchangeable, that you can reflect over the y-axis first and then take that and reflect it over the x-axis, and you get the other part of the graph. But the algebraic test for this one, for odd functions, what happens is you start off the test the same, like f of negative x. And what happens is that it comes out to negative f of x. So you can pull the negative out of the function, sort of, right? That's kind of how you can see it visually. And so like if we test this on the x cubed function, right? So let's say that we label this function f of x is x cubed. Then since x cubed is odd, this property holds, right? So we would have to say f of negative x on our x cubed function. So we replace our input is negative x. So we're going to put in negative x and then cube it. So we have negative x and then we cube it. Well, we know that this one, like if you do negative x times negative x times negative x, definition of cubing something, this comes out to negative x cubed, right? And the x cubed without the negative is the original function, right? This x cubed, like that. So I replace it with the function. And so because this property holds for this function, the function is odd. And so this part of the property of odd functions is what's being applied to the trigonometric functions for sine and tangent. Okay, so if I flip over to the identity, and maybe it'll help here that if I split this, the property of the even function was f of negative x is equal to positive f of x, right? So that's how you can see it with the cosine function. And the property of the odd function is that f of negative x comes out to negative f of x. So you can see that with the sine and tangent, and in turn, they're reciprocals. So we have our input is a negative, and it is the same as if we pull the negative out in front and took it of the positive angle. All right, so let's try to practice how this works, why it works, specifically for specific angles here. All right, so I do want to change one of these example 3s. If you guys can, add a negative in front of the sign on part A. All right, so then we're gonna look at comparing this example 3A, that negative sine of 30, let's calculate that and then individually calculate sine of negative 30 degrees. And this looks like it's following this odd identity for sine. So they should come out to be equal values, right? So let's go ahead and find sine of 30 degrees. So we map out a 30-degree angle. Let me do that. Okay, so we go, here's positive 30 degrees. And we drop this down, create our right triangle. So we have this coordinate point is longer on X, root 3 over 2, shorter on Y, so it gets 1/2. And so if we want the sine, like our sine is going to be the Y coordinate, right? So if we do, this is, okay, so negative sine of 30 degrees is equal to, we still have the negative, and then the sine of 30 degrees is the 1/2. Okay, so this is coming out to negative 1/2 as a final answer. Versus, okay, let's look at sine of negative 30 degrees. So we'll map out negative 30 degrees. That would be a clockwise rotation because of the negative angle measure. Okay, so then this coordinate point goes, it's long on X, short on Y, but negative because we're in quadrant 4. And so the sine of negative 30 degrees is just negative 1/2 because this picture is already drawn with this negative 30-degree angle. So this answer right here is just equal to negative 1/2. So you can see how these are exactly the same. That, like, for example, if I wanted to find sine of negative 30 degrees, if I want to use this identity here, I can just actually find sine of the positive 30 degrees and then put a negative in front of it. And it would be the same answer. And let me just summarize here that sine of negative 30 degrees was the same as sine of, as negative sine of positive 30 degrees, which is negative 1/2. All right, so let's take a look at our even function, which is cosine. So we'll compare cosine of 120 degrees versus cosine of a negative 120 degrees. And if we look at our identity for this one, whether the angle is positive or negative inside the cosine function, it should be the same. We end up with the same value. Okay, so let's find cosine of positive 120 degrees. So if we map it out, the angle, draw the picture, the positive 120 degrees is terminates up here. And we measure, it was measured like this. Here's 120 degrees. It's a little bit past 30 degrees past 90. And we draw our right triangle. And so it's short on the horizontal leg, so negative 1/2, and then positive root 3 over 2 for y. So cosine of the angle 120 degrees turns out to be 1/2. Okay, so cosine of 120 degrees is negative 1/2. Sorry. If we look at, having a negative angle measure, then let's go ahead and draw out this angle. So negative 120 degrees will go clockwise 120 degrees. So 30 degrees past 90 in rotation, right? So you would end up over here in quadrant 3. And that was a clockwise of 120 degrees, so negative 120. And drawing our right triangle here, let's go up to the x-axis, create our right triangle, and this comes out to negative 1/2 and negative root 3 over 2 as our coordinate points because of the leg lengths. The x is shorter than the y. And so the cosine is our x coordinate. So cosine of negative 120 degrees is negative 1/2, which is the same as what we got for the positive case. And you can see why they would have the same, even the same value, even just through the picture, because you can see that the cosine comes from the x, and you can see the x comes from the horizontal leg, and they actually share that same side right here, right? Because through the symmetry, it's a reflection over the x-axis, and you can see that this horizontal leg gets shared for those two angles. So then that's why they're both coming out to negative 1/2. Any questions so far? I think this is a good place to take a break before we go into the Pythagorean identities, which is like the most important identity that you'll learn in trig. And it gets carried on throughout, like if you're taking calculus and stuff, you'll see it again and again. So let's go ahead and take a break here, about 10 minutes. So we'll resume at 11:30. All right, so let's go ahead and continue with learning the Pythagorean identity. All right, so this one's pretty important. So I'll show you how we derive it. So let's recall, our definition for sine and cosine for some angle in standard position. So the definition for sine is that it's y divided by r. Cosine, it's x divided by r. And then r, the radius, is the square root of x squared plus y squared. So using the combination of these three, these three what do you call it, definitions, we'll find the Pythagorean identity by using the Pythagorean theorem on the unit circle. So on our unit circle, r is equal to 1. And so, these definitions, sine of alpha is y divided by r. Since r is 1, then we have that y is equal to sine of alpha, and that's why the y coordinate is sine on the unit circle. Cosine of alpha is x divided by r. So x comes out to be cosine of alpha since r is 1. So if we look at this picture of our unit circle, let me just change this angle to alpha instead of theta. When we have this right triangle that gets formed with some coordinate point xy, our x is cosine of alpha, is the length of x, and y is sine of alpha. So if we do Pythagorean theorem on this picture, we get the Pythagorean identity. So let's use so this would be x squared plus y squared is equal to 1 square. And then we'll substitute our x and y as our cosine and sine. And so let's do this. Cosine of alpha, that whole thing gets squared for x. For y, it's sine of alpha, and that gets squared, and then that's equal to 1. And this cosine of alpha quantity that's squared, another way to write it is just cosine square alpha. Those are equivalent. So usually when we're like squaring trigonometric functions, we write it as cosine square alpha. But what it really is like cosine alpha, if we square it like this, let me do it in a different color. Yes. Oh, you can, but I just calculate, like squared out the 1, it's just 1. Yeah, thanks. So cosine of alpha, that whole thing square is like cosine alpha times cosine alpha, like the definition of when you square something, you multiply it out that to the as many times as the exponent says. And then we just write this as cosine square alpha. Right, so that's what that notation is. And then similarly, sine alpha and squared is sine square alpha. And then that's equal to 1. So this result is actually the Pythagorean identity. Which is given on the next page. So right here, this is the identity in the box. It goes, if alpha is any angle or real number, then sine square alpha plus cosine square alpha is equal to 1. That's the Pythagorean identity. And So let's see how we can use this identity. So if we look at example 4, it says here, find sine of alpha if we're given like that we know cosine of alpha is -2/5 and alpha terminates in quadrant 2. Okay, so because like if we take a look at this identity that we want to use, we know that cosine of alpha is -2/5. So that this -2/5 can be replaced into the second term in the identity. And so we'll start this off. Let's use the Pythagorean identity. Okay, so sine square alpha plus cosine square alpha is equal to 1. And we're going to use the fact that cosine of alpha is -2/5. So the -2/5 is going to be placed in for this cosine of alpha, and then you square it. All right, so this is going to be sine square alpha plus -2/5 square is equal to 1. Right, so when you have just like before the new notation I just introduced, like this is cosine square alpha is the same as taking cosine alpha and then squaring it. So I'm just placing this with the given, the -2/5 for the whole thing, and then it gets squared. So that was the replacement for that cosine alpha, and then we had to square it. So now that we have our equation here, you can see that we can isolate this equation for sine alpha, and that's what we're trying to find. So let's take this equation and isolate sine of alpha. Okay, so that would be sine square alpha plus 4/25, right? Just square it out is equal to 1. And since we need to isolate sine, let's subtract 4/25 from both sides. So we get sine square alpha is equal to 1 minus 4/25. And so 1 minus 4/25 is 21/25, right? Get the common denominator, 25/25, and then subtract out the 4/25. Okay, so we have to get the sine by itself. So we got to get rid of that square, that exponent. So to undo that exponent, we have to take the square root. So sine of alpha is equal to plus or minus the square root of 21/25. So now because we're in like graphing things on the XY plane in standard position where you can have like negative values or positive values depending on the quadrant that you land on, we have to put the plus minus, just like, if you had something like x squared is equal to 10, when you take the square root of both sides, you would say plus or minus the square root of 10. And that's because we're on a XY plane. All right, but there's only one answer here. Is it going to be the positive answer or is it going to be the negative answer? And that depends on what I mentioned before. It depends on which quadrant you land in. So if we go back to the original problem, we were given that the angle alpha terminates in quadrant 2. Okay, so let's go ahead and draw a little sketch, okay? Alpha terminates in quadrant 2. So if we draw like this, and just draw like just any alpha angle like this. Doesn't have to be a 30 or 45 or anything like that. Let me try to, okay, something like this. And there's our alpha angle. This is where we're going to start using that all students take calculus. That tells us the sign of all the trig functions depending on the quadrant. So if we go all students take calculus and we're in quadrant 2, this is telling us that sine is positive. So we're going to take this positive sign because this is because alpha's in quadrant 2. Right. So this all students take calculus. This is like quadrant 1 for all. That means all trigonometric functions are positive. In quadrant 2, the S means sine and its reciprocal, cosecant, are positive. All the other 4 trig functions are negative in quadrant 2. T, so tangent and its reciprocal, cotangent, are positive. All the other 4 are negative. Quadrant 4, cosine and its reciprocal, secant, are positive. The rest are negative. All right, so that's where this piece of information comes into play of where the angle terminates in. All right, so then one last step is to write out sine. So sine of alpha, sine of alpha is going to be positive square root of 21 over 5. Okay, so this is like, I took the positive symbol and I simplified this square root, break up the square root, one for the numerator and then one for the denominator. And this denominator, square root of 25, is 5. All right, so that's how we can, like one way that we use the Pythagorean identity. And you can see that this identity is in terms of like sine and cosine, right? Sine square plus cosine square is equal to 1. But this identity actually has 2 other forms that involve like the other 4 trig functions like tangent and cotangent, cosecant, and secant. And we're going to derive those in the next couple of examples. So example 5, it says to use the identity, the original identity, to show that the next form, 1 plus cotangent square alpha is equal to cosecant square alpha. This is like another form of the Pythagorean identity. So if we start off with the original identity, like that, and I want to get to a point where I get these other forms. Like, so let's just isolate this. I want a cotangent square to appear. Okay, so if I want a cotangent square or cotangent to appear, we know that through the quotient identity, we know that cotangent of is cosine over sine, right? So we want to divide by, since right here we have a cosine square, we want to divide by sine square, and that would give us a cotangent square. So, but we can't just divide the one term. We have to divide the equation throughout by the same thing, right? So we're going to divide this equation throughout by sine square. So if we divide throughout, then algebraically cleaning this up, we can split the left-hand side for each side to have that denominator. So we have sine square alpha divided by sine square alpha plus cosine square alpha divided by sine square alpha is equal to 1 over sine square alpha. All right, so simplifying this sine square over sine square, when you have the same term in the numerator and denominator, that is 1 plus cosine over sine is cotangent, but they're squares. So this is cotangent square alpha. And we know that also one of the reciprocal identities is cosecant of alpha is 1 over sine alpha. All right, so this is equal to cosecant square alpha because we have a sine square. And see how that matches what we wanted to find, which is one of the other forms of the Pythagorean identity. If you want some more convincing of why is cosine square over sine square cotangent square, I can add in this little note on the side that if you have cosine square over sine square, we can write this out like cosine alpha times cosine alpha divided by sine alpha times sine alpha. So like expand out the exponent and you can see that there's a cotangent. And then there's like, here's another cotangent. And so cotangent times cotangent, that gives us cotangent square. And similar for the 1 over sine square, you can break that up in 1 over sine square times 1 over sine square. And each one of those are cosecants. All right, so the next example is deriving the other form. So the other form has a tangent and a secant. So just like before, we're gonna start off with our original identity that sine square alpha plus cosine square alpha is equal to 1. And since we want to get this other form that involves a tangent, well, we know that tangent is sine over cosine. Right? So if I want the tangent to appear, then I want this sine over cosine square like that. So let's divide throughout by cosine square because, you know, with the property of equality, if you do some operation on one side, you have to do it also on the other side of the equation. I just want to, okay, so on both sides of the equation, what we're doing is just dividing by cosine square alpha. All right, and then we can simplify this out. So we'll break up the fraction. We have sine square alpha divided by cosine square alpha plus cosine square alpha over cosine square alpha is equal to 1 over cosine square alpha. So sine square over cosine square, by the identity, it comes out to be tangent square. And then cosine square over cosine square is 1. And is equal to the other 1 over cosine is secant square alpha. And there's the other form of the Pythagorean identity. So they're in the box right here, right below, all grouped together. These are all Pythagorean identities. In all three forms. And these come up so often, like in this class and all your future math classes, you're going to see Pythagorean identities. And so they do have to be memorized. And the thing is, like, see how these two that we just derived stemmed from the original one that was sine square plus cosine square is equal to 1. So I personally, I don't have these memorized. I only have the sine square plus cosine square equal to 1 memorized. And if I need these other two, I know how to get them, right? You're just going to divide by either sine square or cosine square to get, the tangent or cotangent. So like in this class, like you can already see that in this section, we had introduced a lot of different kinds of identities. Like there was the reciprocal identities, there was the even and odd or the negative identities. There was the quotient, right? So here's the reciprocal, here's the quotient, even and odd, and then now this one, and then later in chapter 3, we're gonna add on a ton more. And so like, and you have to be able to recall all these things, because you're going to be practicing so many examples, you end up memorizing it. And so like for me, like I want to memorize the least amount, enough to make a good tool bag to get all the rest of them. And so you don't like cloud your mind with like too many things to memorize. You miss a negative, you miss a sign or something. So my suggestion is to memorize just this first one and know how to get the other ones from it. All right. Any questions about this section before we move on to chapter 2? All right, so I did have the chapter 2 notes uploaded on Canvas a while ago. So if you want to go grab it now, you can. So chapter 2, in this chapter, we're going to introduce, like in the first section, this radian measurement, some applications to that, and we're going to start graphing these trigonometric functions. So let's start off with just section 2.1, the radian measure. And so, as I had mentioned earlier, that radian is another way to measure an angle. Like so far, we've been just using the degree measure. And so these two different kinds of measurements for angles, just think of like in terms of a length, it's like feet versus inches, right? So we have degrees versus radians. And so the way that a degree measure was formed is that they took a circle and cut the circle up into 360 identical pieces or arcs. Like this is an arc, right? So if you cut this up, the circle into like 360 even pieces, right? Oh, that was a bad one. Like that. Each of these arcs got 1 degree, and there's 360 of them. And that's how we have that one loop around the circle is 360 degrees. The way that they came about is like back in like way back, like in old times, the people were trying to measure like how many days in a year there are. So there's no computers or anything. They're like sticking a stick in the sand and like kind of measuring the shadows that the sun is creating. And they found they estimated that there were 360 days in a year. But with newer technology, doing that same experiment differently throughout time, we find out that there's 365 days in a year. But that's pretty good considering that they're putting a stick in the sand and like measuring shadows and stuff. So anyway, so that's how we got the 360 degrees, and for one loop around the circle, and we just stuck with it. So that's how we got the degree measure. The radians is our alternate way and to measure angles. And the way that we measure the radians, what we do is we take this circle, right? And it has some sort of radius. And so if this was radius is a piece of string, and we have this piece of string that's bendable, and we start using that string to get the edge of the circle, that's called the arc length. So this arc is the same length as this radius, just bent to get the edge of the circle. And it's like, how many of these do we need to go around the entire circle until we close it? Well, it turns out it's about 6 and a little more, right? So these are all the same length. So it's like you needed 1, 2, 3, right? All the way 6 and a tiny bit more. And so if you recall from geometry that the circumference of a circle, that's like the perimeter, right? The edge of the circle like this, or going around the circle, it's 2 pi r. If we fix r to be 1, it's really actually okay. I just saw Miguel's comment. Anyway, so if we see that oh yeah. So if we just forget the R, the because it gets scaled to the same amount. Like if this radius was 5 versus the radius was 1, you're gonna have by this the ratio is maintained that you're gonna need 6 and a little more to go around, like make a full loop with that sort of radius. It's proportional. So then if we calculate this part, the 2 pi part on the calculator, right? 2 pi as a decimal, it's about 6.28. The 0.28 is that little bit more. All right. So, we like to have conversions like, there's 12 inches in a foot, right? So how do we convert like degrees and radians? Well, the relationship is that 360 degrees is equivalent to 2 pi radians. And so that was like, we know one full loop around is 360 degrees. If we did that in the equivalent radian measure, the 6.28, that was 2 pi. So that's where this conversion factor comes in. So later in the later exercises, we'll do some unit conversions between the two measures, radians and degrees, or degrees to radians. But let's kind of revisit our unit circle here. So here we have our unit circle, and you can see that we have our common angles listed. So let's go around the circle and do the radian equivalent. And I'm going to show you how I do it. And it has to, like, just like before, it's about like cutting the circle into like equal pieces and dividing pi by those equal pieces. So let's start off, where 0 degrees is, that would be the same starting point, the initial side. It would be 0 radians. If we made one full loop around the circle in radians, that was 2 pi, right? The circumference, it was 2 pi if you do one full loop. All right, well, if this whole thing is 2 pi, what if we only did half, right? That would be half of the 2 pi. So this would be pi. All right, so those are some good marking points. Let's do our quadrantal angles. So if I zoom in, and let's just focus on the top half of the circle. All right. So I look at, let's do this. All right, I look at the top half of the circle, and I know, over on the initial side, that's 0. And if we do a whole semicircle, like half the circle, we end up at pi, right? So what if I cut that in half? Then that would be, you took pi and you halved it, pi over 2. Right? All right, so that was the top half, but let's continue counting by the halves around the circle, right? So if I zoom out, then this was like 1 pi over 2 is at where the 90 degree is. Then 2 pi over 2, well, that reduces to pi. If I go another half around, that would be 3 pi over 2. And I go around, that's already simplified. Do the full loop, that would be 4 pi over 2, which that simplifies to that 2 pi. Right? So when you're going around the quadrantal angles, you're counting by halves. Okay, so those are all the quadrantal angles covered. How about we go through, let's go through the 45-degree increment. So again, we're gonna kind of zoom up here, only look at the top portion of the semicircle. And remember that the 45-degree angle, so like if the 45-degree angle takes a quadrant and cuts it in half, right? So if I look at the top half of the circle, we cut the circle into 4 equal pieces, 1, 2, 3, 4, right? So the 45-degree angles are going to be in quarters, right? We're going to cut this pizza up into quarters. So the first 45 degrees would be a quarter of pi, which is pi over 4, right? And then if we do the next quarter, that would be 2 pi over 4. You're at the 90-degree mark, but that's pi over 2, right? When you simplify it, the 2 reduces by half or 2. And keep counting up around the circle. So this is 3 pi over 4 is 135, equivalent to 135 degrees. And then 4 pi over 4 reduces to pi. So, you do want to get those quadrantal angles matching up when it gets reduced. All right, so 4 pi over 4, keep counting up. 5 pi over 4 is equivalent to 225 degrees. 6 pi over 4, we're counting by quarters here. Reduces to 3 pi over 2. Okay, 7 pi over 4 is the next quarter. That's already reduced. And then the full loop around is 8 pi over 4, which that's 2 pi. All right, so that's the 45-degree case. So 45-degree angle cases, you're counting by fourths because we cut it into 4 equal pieces on the top half. All right. So let's take a look at our last case, which is the 30-60. So the 30-60, if we zoom into, again, the top half, all right, so we look at this top half of the circle. And when we were looking at the degree case and we looked at one quadrant, we were cutting the quadrants into thirds, right? Like if you cut each quadrant into 3 equal pieces, that's how you get the 30 and the 60. So if we look at how many pieces there are on the top half of the circle, that's 6 equal pieces, right? So it's like, oops, each piece, there's 1, 2, 3, 4, 5, 6. So each piece gets pi, like pi over 6. All right, so if we go around the circle, starting from 0, the initial side, we go to the 30 degrees, and that's 1 pi over 6, or just pi over 6. And we go to the next slice, the 60, and that would be 2 pi over 6, but that reduces to pi over 3. Okay, so the 60 degrees is pi over 3. You always want to use the reduced format. Okay, and keep counting up over 6. So the next one, 2 pi over 6, 3 pi over 6. We know that reduces to pi over 2. Okay, and the next one, 4 pi over 6. That's 2 pi over 3 when you reduce it. And 5 pi over 6 is equivalent to 150 degrees. And that's already reduced. And then we have 6 pi over 6, which we know is pi. All right, and then keep counting up. So the 210 degrees is the next, sixth of a slice. So that would be 7 pi over 6. Okay, and then 8 pi over 6 is equivalent to 240, but that reduces to divide by 2, 4 pi over 3. Okay, and keep counting up. So next one is 9 pi over 6. which, yeah, that reduces to 3 pi over 2. Okay, so 10 pi over 6 is the next one, and that reduces to 5 pi over 3. And then the next one is 11 pi over 6, which is fully reduced. And then the last one is 12 pi over 6, which is 2 pi. All right, so that's kind of how I approach, filling these angles in, because you don't want to convert radians and degrees for these common angles, because they are so common that it's a pain to always be doing unit conversions from one measure to the other. So the approach is cut the circle up into either halves, like half, count by halves for the quadrantal, count by 1/4 for the 45 degrees, and for the 30/60, count by sixes. All right, so we'll practice this some more, but you do want to get fluent to the point of like, okay, I need to find like cosine of 300 degrees. Well, it'll say like cosine of 5 pi over 3, and you have to be like, oh, okay, 5 pi over 3, count, that's the over 3 or over 6 is the counting by sixes. So I would count, until I hit 10 pi over 6 or 5 pi over 3. And then I know, since I'm graphing these things accurately, that it would be a 60-degree angle in quadrant 4. So we'll get to that in a later example. All right, so we'll kind of step away a little bit and take a look at converting from radians to degrees or degrees to radians, example 1 and 2. So the first example says to convert 48 degrees into radian measure and give exact answers, which means like a reduced fraction in terms of pi would be considered exact. So let me just write the conversion up. 360 degrees is 2 pi radians. That's the conversion factor. And with any unit conversions that you're doing, like if you're in a chemistry class, there's a lot of unit conversions. The name of the game for unit conversions is to cancel out the units until you get the units that you want. So for example, if I start off with the 48 degrees, the thing we want to convert, and we're gonna multiply by some conversion factor, and in the end, we're trying to convert it into radians. So I want the radians to be at the end. So in this case, we are going to have to multiply, and right here, this conversion factor, one of these are going to go in the numerator, one of them is in the denominator, and how you pick is like how the units cancel. So if I need the degree measure to cancel, then I need the degree measure to cancel out with a degree measure in the denominator, right? So then what's attached to the degrees? 360. So 360 goes in the denominator, and 2 pi radians is in the numerator. And so you can see that the degree measure, these units cancel out, and what we're left with as a unit is radians, and that's what we want to end up with. So when you're doing the conversion, it's like you're multiplying by 2 pi and dividing by 360. And so if we calculate that value out, because we want the exact answer in terms of pi, I'm going to carry the pi over and then calculate out this 48 with the 2 and the divide by 360, right? So 48 divided by 2, or no, 48 multiplied 48 times 2 divide by 360 is 4/15. Okay, so it's 4/15 pi. And that's in radian measure. All right, and example 2, we're going to convert from radians, 11 pi over 12 radians to degree measure. So that's going to be, let's start off with what we have. So we have 11 pi over 12 and radians. So the units are, when you were given the units like that, that is in the numerator. So I'll write it like that. The 12 is in the denominator. And then we're going to have to multiply it by our conversion factor. And our goal is to have degrees at the end of it, right? So that tells us that the radians has to be in the denominator because we want the radian measures to cancel. Well, what's attached to the radians is 2 pi. So 2 pi radians has to go in the denominator and 360 degrees is in the numerator. And see how, yeah, we want the degree measure to stay because that's our goal, is to have a degree at the end. So if we calculate this, we see that also actually these pi's cancel. So 11 times 360 divided by 24, right? The 12 times the 2 in the denominator. So divide by 24. This calculates out to 165 degrees. Right, so you can check it on your own through your calculator. The multiplication, it should come out to 365 degrees. So the equivalent of 11 pi over 12 radians would be 165 degrees. All right, so oops. Let's do a couple of these examples. And for example 3, this is the same goal as how we opened up the class. So we're going to find the exact value of these trigonometric functions. But now you can see that the angles are measured in radians. So just like before, like at the beginning of class, we're going to measure out the angle, create the right triangle to find the coordinate points, and then choose the coordinate points appropriately, like cosine is X, sine is Y. All right. So let's map out 3 pi over 4. Okay, so 3 pi over 4. So denominator is 4, which means we're cutting in quarters that's linked to 45-degree angles. So what I'm going to do here is actually go around the circle, or what is it? Start from the initial side and make my cuts of fourths until I get 3 pi over 4, right? So if I start here at 0, then the first cut is pi over 4. Okay, this is 2 pi over 4. And then the last one is where we terminate, is 3 pi over 4. Okay, so let me just, okay, there's our little sketch. And so where we terminate that angle measure was the counterclockwise rotation from initial to terminal side, 3 pi over 4. And then we terminate, and then we drop down. So we take this terminal point and we drop it down to the x-axis, create that right triangle. And we know that this is a 45-degree angle because we were cutting it in equal fourths. And so we know that this coordinate point is going to be negative square root of 2 over 2, comma, positive square root of 2 over 2. And because we want the cosine, we would take the x coordinate. Okay, so cosine of 3 pi over 4 is negative square root of 2 over 2. All right, so let's do another one. Let's take a look at sine of negative pi over 6. Okay, so it's negative, which means that we're going to measure pi over 6, but in a clockwise direction to account for the negative. So we know that pi over 6, if you look at this, the one little sliver of pi over 6 is a 30-degree angle equivalent. So we're just going to make our 30-degree, but clockwise, and that would be a pi over 6 slice that's negative. All right, so this is like 1 pi over 6 is that 30-degree angle equivalent. So that rotation is negative pi over 6. And then we'll draw up to the x-axis. And we have our right triangle. So the longer side is the x coordinate. Shorter side gets the 1/2 on the y coordinate. And because we need the sine, we take the y coordinate. Okay, so sine of negative pi over 6 is negative 1/2. All right. So I think this is a good place to stop, and we'll, continue this example next week on Tuesday. But I believe that, I have like you can be able to do a lot of this homework for 2.1. So make sure that you're working on it so that, for the due date, like when we finish it off on Tuesday, you can just cover the ones that, this example would cover for the rest of the homework. All right, so have a good weekend. I can stay for a little bit if you guys have any questions. And if not, then I'll see you on Tuesday.
Bye, Professor. Have a good weekend.
Thanks, Jessica. You too. Bye, guys. Have a good weekend. Does anybody have a question before we end the meeting? Bye, Miguel.